Welcome to Empowered Learning. This video will be about the process called reduction of order and how we use that particular technique to be able to find another solution to an ordinary differential equation when we already know one solution to that particular equation. So before we actually get into the reduction of order process or method, I want to talk about a few foundational things just to make sure that our minds are in the right place and we have the right perspective whenever we think about this particular technique. So in general, this particular technique is one that is used, but if you're taking a first year or introductory differential equations course, you are going to use it. But as you move further on into the course and you learn how to solve higher order differential equations, such as, let's say, second order linear ODEs with constant coefficients, or ones where you have higher order linear homogeneous equation or non-homogeneous type of equations, we will already have this process of reduction of order sort of baked into it. So it's not something that you're going to necessarily have to do over and over and over at this stage. But for those of you that will eventually end up studying higher mathematics, let's say advanced mathematics, and you're having to apply these sort of things to, let's say, like wave equations of the sort, then you'll see that we do end up having to do this whole reduction of order process again at those higher stages of math. Okay. All right. So the first thing that I want to call to your attention here, and as you can see, I have this chart here, and the main reason why I'm showing you this is because at its core, the reduction of order method is really just another substitution technique. And so when we learned about first order substitution techniques, of course, we had one that was linear substitution, which is what I'm showing here. Of course, we had recognizing a first order homogeneous equation. That was essentially an equation where we said, hey, we have a suggested substitution, and the y is equal to u times x, or u is equal to y divided by x was the one for that one. A Bernoulli equation is really just a first order linear equation, but it, as I like to say, has an identity complex because it has this y raised to the n here. And of course, the suggested substitution is to let u equal to y raised to the 1 minus n. And thus we know that y is going to be equal to u raised to the 1 divided by 1 minus n. Now, again, the point that I'm getting at here is that reduction of order will have a suggested substitution, just like these particular types of equations have their suggested substitutions to make everything work. And so that's the first thing I wanted to call to your attention here. I also want to say that these same kind of techniques here, we saw that we used some of those techniques, not the same, but very similar to some second order ordinary differential equations as well. And so if you're kind of following the videos in the order that I've intended for you to watch these, you would have already reviewed the introduction to second order or higher order ordinary differential equations and solving them by substitution methods. So this is just the next one after that. And again, the point I want to make is we have all these substitution techniques. Reduction of order is just going to be another one. The thing that's special about the reduction of order one is that we're actually going to use what we know as our known solution to help us figure out our new solution. Okay. And of course, when we go over the steps, you'll actually see that. Now, we see that these techniques here, these types of equations here, and the corresponding substitution techniques, they're only for a small, set of equations. And of course, the ones that we see in applications a lot are really second order ordinary differential equations and higher. And so even with the substitution techniques that I talked about with the second order ones, we see that that's really like a small set of equations that we actually use it for in actual practical applications. However, this reduction of order method that I'm going to talk to you about in this video and some of the other ones as part of this series is something that we use, but it is something that's foundational again. And we're going to see that once we know how to do it and we move on to studying different types of higher order ordinary differential equations and solving them, that'll just kind of be baked in the process. So the other major thing that I wanted to talk about before we actually got into the process of reduction of order is to define what a higher order linear ordinary differential equation is. And so it's important for us to know what these types of ODEs look like versus just a regular higher order ordinary differential equation because of the fact that these are the types of ordinary differential equations that tend to show up a lot in applications. And so you're going to see that we are going to use this reduction of order process a lot with these types of ODEs. So in short, I just want you to recall here that whenever we had an equation that looked like this, we called it a first order linear. Okay. Of course, it can also look this way as well. A second order linear ODE will look something like this. And so the main thing to see here is, do you see how we have the second derivative, then the first derivative, then no derivative, and then some function? And so all second order linear ODEs will have this pattern of, we have a term that has a second derivative of the function that we're trying to find, then the first derivative, then no derivative, and then of course another function here on the other side. Okay, so that's one thing. The other thing is that these coefficients that are here, they are either going to be constant values or they are going to be functions of x. Okay, and that is the only thing that they can be if they're going to be classified to be second order linear ODEs. Okay, again, we have second derivative of y, first derivative of y, no derivative of y, and then some function here. And of course, this could be either a constant or a function as well. If this is going to be a function, it is also going to be a function of x, just like these coefficients here. Okay. So again, these coefficients, they can either be constants or they can be functions of x only, or functions of whatever the independent variable is. Okay. Of course, for a third order linear ODE, kind of follows suit. Got third derivative, second derivative, first derivative, no derivative. And all of these coefficients that you see here on the left are either constants or functions of the independent variable, which we're just calling x. And this function, or g, could either be a function of x or a constant as well. Okay. Now, of course, in general, this is what your nth order linear ODE looks like. Of course, you have the nth derivative, nth minus 1, nth derivative, all the way down to no derivative. And of course, you got your function g on this side here. Okay. So that is what in general, nth order linear ODEs, what they look like. So for example here, you can see that we have examples of what second and third order linear ODEs look like. So of course, this first one, second derivative, first derivative, no derivative. And here we have a coefficient of 1. Here we have a coefficient of x cubed, which is okay, because remember, the coefficients either have to be constants or functions of the independent variable. Here, another function of the independent variable, and g is also a function of the independent variable, which is x. For this next one here, we see that this is a second order linear ODE where all of the coefficients are constants. Okay. Here is an example of a third order linear ODE where all the coefficients are constants. And for this one here, we see that this is a third order linear ODE. And in this case, we see that these first three coefficients are functions of x. Last one here is a constant. And of course, our function g on the other side is a function of x as well. All right, so let's look to see what some counter examples are to this, okay? So here in this particular ODE, we see that we have a coefficient that is a function of y, okay, not of x. And so because of that, we do not consider this type of differential equation to be a second order linear ODE, okay? For this one, the issue here is that we have the first derivative of a function being squared, okay? Even though we have second derivative here and we got first derivative over here, notice that this first derivative squared and it doesn't follow the same kind of profile as, let's say, this one, okay? Where we had second derivative, first derivative, no derivative. And notice that none of these had, let's say, y, let's say, the derivative of y with respect to x squared or cubed or anything like that, okay? All right, again, for the next one, same situation as the first. We have this particular coefficient here as a function of y, got the same problem here. And for this last one, got the same problem here, okay? So now you know what second and third order linear ODEs look like. And you have examples for that as well as what they don't look like. All right, so the last thing that we want to talk about before we actually go into the reduction of order process is to determine what do we mean when we say homogeneous versus non-homogeneous for higher order ODEs, okay? And so the point that I'm making here is that if you remember in the first order ODEs, we had a certain type of homogeneous equation here where if we had dy over dx, this would be a function of x and y, and this would be the same as if I was to let x be tx, and if I would let y be ty. If my equation met this condition here, then I could call it a first order homogeneous equation. And in knowing that, we would say, hey, let y equal u times x, or better yet, let u equal y divided by x. And then, of course, figure out what y prime is, and then make your substitutions, okay? So this was the rule for the first order homogeneous. When we get into the higher order homogeneous equations, this meaning here no longer exists, okay? So my point is first order homogeneous is different than second, third, fourth, fifth, sixth, and so on homogeneous. For the higher order homogeneous equations, it's just real simple. And that is that function g that we've been talking about, that's been on the right side of the equation. If g ends up being 0, like how you see here, even though these aren't, linear ODEs here, but if g is equal to 0, then of course our ordinary differential equation is assumed to be homogeneous at that point. If it's something other than 0, like a function of x or whatever, then it's considered to be non-homogeneous, okay? So just know from now on, when we talk about homogeneous ODEs and we're talking about second order and higher, all we're just saying that whatever the ODE is, it equals 0. And if it's, let's say, some ODE where on the left side it's something, then it equals, and then let's say it's a function of x on the other side, then it's going to be non-homogeneous. All right, so let's get into the actual process of the reduction of order technique for second order linear ODEs. And so being very specific here. So when we have a second order linear ODE, and of course, we can kind of follow suit if we have a third order, fourth order, fifth order. But the main thing is that it is a higher order linear ODE. If we have that specific type of ordinary differential equation, the technique that we're going to study here is how we actually do what's called reduction of order. Okay. And again, I want to remind you, the purpose of the reduction of order technique is for you to find another solution, meaning another function that you can plug into your differential equation that will satisfy it, just like the one that you already know. Okay. And so for the reduction of order process, in order for you to start that process, one of the things that you are going to have to know is a known solution to that ODE in the first place. So that's why in step one, it says, given that y1 of x, which we're just going to call y1 for short, is a known solution to your ODE. Now, if we know that, and we know that we're dealing with a second order linear ODE in this case, then we essentially say, well, hey, we're going to assume that the second solution is going to be u times y1. And of course here, u is assumed to be a function of x. So as you can see here, the suggested substitution is that I am going to assume that my second solution is a product of the first function that a product of the solution that I already know times something else that I don't know. Okay. Now, what is the purpose of doing this particular type of substitution? Okay. So one of the things that we want as a result of finding another solution that's going to satisfy the differential equation that we're working with here, in particular the second order linear one, what we want is for this y1 and this y2 to be what we call linearly independent. Okay. Now, what that phrase linearly independent, if we look at it from a mathematical point of view, all we're just saying here is that if I wanted to come up with a formula to kind of characterize all the solutions that I had, then I could say if I take y1 multiplied times a constant plus y2 and multiply times a constant c2, then any linear combination of these two functions here will give me any solution that will satisfy that particular ODE. Okay. Now, if we look at it from from a more conceptual understanding here, when we say y1 and y2 are linearly independent, what we're actually saying is that y1 and y2 are two functions that are different from each other, but they're not constant multiples of each other. Okay, so I'm going to give you an example of that. So let's say here that y1 was 2 e to the x. And let's say y2 was 2 e to the x minus 3. Okay. So here, if you notice, these two functions are relatively similar to one another because of the fact that I could just come here and say, hey, well, what is the difference in between these? Well, it's just going to be a constant. Okay. Another way that I could, look at this is if I was to divide this function by this one, I would end up getting some kind of, constant multiple or something like that. Okay. So, but the point here is that if I had something like y1 is equal to e to the 2x, and let's say this was x times e to the x, then of course, if I was to take these two and let's say I subtracted one from the other, I'm not going to get a constant value as the difference in between them. And if I was to take one and divide it by the other, I'm not going to get something that's going to be I'm not going to get something here that's going to be a constant multiple of each other. Okay. So that's the main idea. So we want something to where one function essentially doesn't have anything to do with the other. Okay. And that's important to understand here, because if this u of x here, if we go through this whole process and this u of x here is just a variation of the theme of what we see here, then really what that's telling us is that our ODE really only has one true function that could serve as what we call a basis of solutions. Okay, and meaning a root function that we could use to either multiply times a constant or multiply times a constant and add or subtract a constant from it to be able to come up with another solution. Okay. So I know I've spent a while here on step one, but it's important to know why you're doing what you're doing here. Okay. So in short, you know what y1 is. You say that y2 is going to be some function u times y1. Okay. Now, everything else is relatively easy. And I say relatively because the devil is in the details, but the actual process itself is relatively easy to understand. So now that we are telling ourselves, hey, we're assuming that y2 is going to look like this, we take the first derivative and second derivative of that function. Okay. And of course, we're doing this because if we're dealing with the second order linear ODE, then that means we have a term in it that has a second derivative of y. We have a term that has a first derivative of y in it. And what we want to do is substitute those first and second derivatives here to be in terms of u and y1. Okay. So we see here that for the first derivative and the second derivative of y sub 2, we just use the product rule to be able to do that. Okay, so this is the result for the first derivative. This is the result for the second derivative. After we do that, then what we do is we simplify our ordinary differential equation by essentially just making what y prime and y sub 2 prime and y sub 2 double prime are, plugging it into our equation. And then from there, we're going to try to combine like terms. Now, in the reduction of order process, we already know, because we're dealing with, in this case, a second order linear ODE, what the outcome should look like. Okay. And that's the good thing about the reduction of order process. Once we do it, we kind of know what to expect. So if we're doing it and we don't get that, then there's a problem. Okay. Either we've done something wrong mathematically in our process, or we have a situation where the function that we're assuming is a solution really isn't one. Okay. All right. So this note here is important, and it says, if given an ODE, if given your ODE was second order linear homogeneous, the result of simplifying after our substitution in step 2 would be a first order separable ODE. And this is provided that we let u prime equal to v. Okay. And of course, we'll follow suit. V prime is going to be u double prime. Now, if the given ODE was a second order linear non-homogeneous ODE, the result would be that we would have a first order linear ODE. Okay. So I'm going to say that again. If what we have to start off with is a second order linear homogeneous equation, after we figure out what y2 prime is and y2 double prime is, and substitute everything into that equation, we are expecting to get a first order separable ODE out of it. Okay. And that first order separable ODE will happen by us making this substitution of letting v equal u prime and v prime being u double prime. Okay. Now, what's going to happen there is that everything that is just in terms of u is going to go away. Okay. And that's how we're able to make this substitution of V be U prime and V prime be U double prime. Even in the sense of if we have a second order non-homogeneous, okay? Remember that homogeneous means that our equation equals 0 if it's second order or higher. If it's non-homogeneous, then the equation does not equal 0. So it's going to be a function of x. And so if we have that situation, then we're going to end up with a first order linear ODE. The thing that's great about this is that we know how to solve both of these types of equations, okay? Especially if you've been watching the videos in succession, like how I've been intending for you to do it. If you don't know how to solve first order separable equations or first order linear ODEs, then you want to go back and watch those videos, okay? All right. So after that, then everything else is just kind of cleaning things up, make it look nice, and get to your final answer here. So for step 4, we want to solve the resulting ODE by using either separable or first order linear equation techniques. Once we do that, we are going to find out what V is, essentially, okay? And remember, in this case, we're going to say that V is equal to U prime, or dy over dx. So if that's the case, then of course, if I wanted to find out what y is, then I would just integrate both sides here. And to be technically correct here with the math notation, if I multiply both sides by dx, what I would have is something like this. And then of course I would have dy here, and I would have the integral there, okay? And so it would, look something like that. And so let's see. Oh, hold on. Yeah. Okay. So we would have something like this. I don't know why I have the dy here. So let me change that. Okay. So yeah, I had dy there, but really this should be du over dx. And so that should be du there. All right. And so what I have here is the same thing that this would be. And of course, the main thing here is to know that if I know that V is equal to U prime, then I just take the antiderivative of whatever this is to find out what my U is going to be, okay? And that'll be done essentially by taking the antiderivative of whatever V is, okay? And so remember, the goal here is to find out what U of X actually is. And so this last step here is going to help us to be able to do that. So at this point, the reduction of order process is technically over, okay? Because we found what that other function is. Now, how we're actually going to use it is, now that we know what U of X is, remember that we said that the second solution to this differential equation should be whatever we just found here times the solution that we already knew of, okay? And so that will help us to be able to come up with the other linearly independent solution to our ordinary differential equation here. And in particular, for this case, the second order linear homogeneous equation. So step 6 here just says that once we find y2 and compare it to y1, we need to make sure that they are indeed linearly independent. That basically they're not going to be non-zero constant multiples of each other. And then step 7 just kind of explains, all right, well, what have we found? Okay? And because each linearly independent solution of our ODE can satisfy this ordinary differential equation on its own, we use the superposition principle to conclude that if I take both of those solutions and do linear combinations of it, what I'm going to have is two functions that form what we call a basis. And a basis is just a set of root functions that you can say, hey, if I take these two, do any linear combination of these two functions, I can come up with a whole family of functions that will satisfy the ordinary differential equation I was trying to solve. Okay? And that's essentially why we do reduction of order, so we can find that second solution to the differential equation, so that we can create this big general solution that has all these functions in it that will satisfy that differential equation. Okay. Now, please note that if we had a third order linear ODE and we wanted to do this process, everything that we just did, we would possibly have to do it twice, because a third order linear ODE would have to have 3 functions that are linearly independent from each other to be able to create a basis of solutions, or create a set of root functions, so that if I did linear combinations of all 3 of them, I would cover any and all possible solutions to that third order linear ordinary differential equation. Okay. All right. So I've talked enough about, setting everything up as far as the perspective and what type of equations that we're dealing with in the process. Let's just go ahead and get into some examples now. All right. So for our first example here, we're going to have a low stakes example. And so I'm going to read the instructions, and then after that, we are going to actually do it. So the first thing that we want to do is identify the order of the ordinary differential equation. We want to say, hey, is it first order, second order, third order, whatever. Okay. Once we know that, we want to know, is that second order or higher ordinary differential equation, is it what we call a linear ordinary differential equation? Okay. If it is, then we want to know, hey, is that second order or higher linear ODE, is it going to be homogeneous? Okay. And remember, linear just means that for the second order, we got a term with y double prime, a term with y prime, a term with y, and then equals, and it's going to be either some constant or function of x here on the other side. Okay. If our ODE is homogeneous, then all that means is that the right side of it equals 0. If our ODE is non-homogeneous, then that means that it's going to be something else other than 0. Okay, and 4x squared is just an example of that. All right, so now that we know that, let's go ahead and look at the actual problem. Okay, so for our first ODE here, we see that we have term with second derivative of y, first derivative of y, no derivative of y, and g is a function of x. And we see that these other coefficients here on the left are either constants or functions of x as well. So this would be considered to be a linear ODE. Okay. Now, is it homogeneous? Again, if it's homogeneous, then that means that the right-hand side of that equation there is going to equal 0. And since we don't see that here, it would not be homogeneous. Okay. For B, you can kind of look at that one. You see I've already answered the question there. The main thing here is that even though I have second derivative of y, first derivative of y, if I was to subtract both sides of this equation here by 4y, then this would be minus 4y equals 0. And of course, we have second derivative, first derivative, no derivative. And then over here, we have 0. Okay. And so that's why, because the right-hand side is 0, that's why it's homogeneous. And of course, second derivative, first derivative, no derivative. And then all of the coefficients here are either constants or functions of x. That's why it's linear. Okay. All right. So for this next one here, we see we have third derivative. We're missing second derivative, first derivative, but we do have no derivative here. Okay. Now, even though it's missing, we still know that it's going to end up being linear. Okay. Because anything that's missing, like the term that has a second derivative, we can just say that that's plus 0 times y double prime. And for the one for the first derivative, plus 0 times y prime. Of course, the order here, since third derivative is the highest, that's going to be 3. And because this equals 0 here, it is going to be homogeneous. Okay. All right, so for this next one here, we see that the highest derivative in any term is a 2, okay? Now, if you were thinking that it was 3, that's not true. This is the first derivative raised to the third power, okay? That's very different than having the third derivative, okay? So the highest order is a 2 here. Because we have a let's say the first derivative of y being raised to some power, we can't write it into a form like this one. So this would definitely not be linear. And then, of course, our equation here is not going to be equal to 0. I mean, we could force it to be that, but it needs to be in this linear form before we start talking about it being homogeneous. So the answer to this would end up being no. All right, so for this next one here, we see that the highest derivative in this particular ODE is going to be of 4th order. That's what the IV means. And we see here that we have a 4th derivative. We don't have the 3rd derivative, but we do have a 2nd, we have a 1st, and then we have no derivative here, okay? So this looks like it's going to be linear. Now, is it homogeneous? I have yes here, but really it's no. And I guess I forgot to correct this. But here, if I follow the profile of what a linear ODE looks like, I can add 25 here to both sides and make this look this way, okay? And so technically here, I got to have it as highest derivative term, next highest derivative, keep going until I get to no derivative. And then, of course, after this, if I have anything else left, I got to put it on the other side to see if it's homogeneous. And so for this one, it would be no for that reason, okay? All right, so for this last one here, this is y raised to the 55th derivative. Again, don't know why we would ever need to do that. But here, one of the things that you are assuming is that every other term past that, up until the no derivative, will be 0 plus y raised to the whatever derivative that would be, okay? So because of that, we would still consider this to be linear, even though it's missing all those terms. But of course, this would not be homogeneous because the right-hand side is going to be something that's not 0, okay? All right, so again, we need to understand what these particular types of equations look like because this whole process of reduction of order only deals with dealing with nth order linear ODEs. All right, so let's get to our first example here. So for the set of examples that I'm going to do here, we're given a second order linear ODE, and we're also given a solution to that ODE. And what we want to do is verify that solution first. And then after that, we want to use this method of reduction of order to find out what the second solution is going to be, okay? And, oh yeah, see, I got a small mistake here. So let me go ahead. This should be a 1, not a 2. All right, so here is our second order linear, and in this case, homogeneous ODE. And here is a solution to it. So to verify that a function is a solution to a differential equation, you just substitute in that function and its corresponding derivatives into it and see does the left side equal the right side. And of course, that's all I do here. So I know that my y sub 1 is e raised to the 2x. So using the chain rule, I take the first derivative and the second derivative here, and then I just plug that information back into my ODE, okay? For the second derivative, I know it's going to be 4e raised to the 2x, so you see that here. For the first derivative, it's going to be 2e raised to the 2x, which is here. And then the original function is just e raised to the 2x, which I plug in here. Of course, on the left side, add everything up. I see I get 0, and that's the same thing that I have on the right. So I know that this particular function here is indeed a solution to this particular equation. So now that we have verified that, I know that I can find another solution, y2, which is going to be suggested to look like some function u of x that I don't know that I'm going to find times y1 of x, the function that I do know, okay? And of course, in this case, it's going to be e raised to the 2x. So now we're actually going to do the reduction of order process here, okay? So first thing we do, again, is we do this suggested substitution, okay? And then we're just going to write it as y sub 1 for short. Or you could just go ahead and just write it as u e raised to the 2x if you want. Go ahead and plug it in. So we take the first derivative and the second derivative by using the product rules here. And of course, you can kind of see me going through all of that, so I won't bore you with the details on it. But this is what the first derivative ends up looking like. This is what the second derivative ends up looking like, okay? And here, since I'm dealing with the e raised to the 2x function, I'm purposely trying to factor everything out to have the e raised to the 2x on the outside, because it's going to help with my simplification later. All right, so from here, now that I know what all that is, I just kind of collect everything to write it so that when I start to substitute this back into my differential equation, I have one place to look. So here, notice that our differential equation was y double prime minus 4 times y prime plus 4 is equal to 0, okay? And so here what I've done is, since I'm actually trying to solve for the other solution, which is y sub 2, I put 2's on these. So that's why you see me doing that there, okay? So all I do now is y sub 2 double prime. I know that it's this, so I write it in place of y sub 2 double prime there. Do the same thing for minus 4 times y prime, y sub 2 prime, which is what you see here, and then 4 times y sub 2 you see here, okay? Now, at this point, this is important, okay? When we substitute this in, because I have a 0 here, I know that this is a homogeneous equation, okay? Second order homogeneous to be exact. Because of that, what I know is that every term that has u in it should be able to cancel out with all the other terms, okay? That's the first thing. The second thing that I know is that this particular equation is going to end up being a separable equation. Why do I say that? Well, let's go back and take a look. So if we go back to our basic process for applying reduction of order, if you remember, we've done step 1 here. Let y sub 2 equal this. Step 2 is we just find y sub 2 prime, y sub 2 double prime. And then we've done the beginning of step 3 here, which is do all the substitutions. And remember here that we said if our ODE was second order linear homogeneous, that the result was going to be a first order separable ODE, okay? And in the equation that we're dealing with, we have a second order linear homogeneous. So I know it's going to be, it should end up looking like a first order separable ODE. And it's going to look like that if I let v equal u prime and v prime equal u double prime, okay? And remember, I told you that what this essentially means is that whenever we do this substitution, all terms with u in it are going to cancel out or go away with the other terms, okay? So we keep that in mind because we need to know what it is that we expect going to that next step. All right, so if we go back to our problem here, if we were to go ahead and factor out e raised to the 2x in all the terms, you'll see that we'll get this step here. And if I group everything in terms of things with u double prime in it, things with u prime in it, and things with just u in it, notice that when I do that, all of this goes to 0. That is what I was expecting. Okay. Now, just for this particular example, I got an extra added bonus, and it ends up that everything in terms of u prime is also going to 0 as well. Okay. This does not always happen, but this always does. Okay. So because of the fact that we have everything in terms of u and u prime both going to 0, all I have left is u double prime. Okay. And by definition, this is a directly integrable type of equation, which basically means I can take the antiderivative of u twice to figure out what u is going to be. Okay. So if I do that, if I know that the second derivative of some function is 0, then that means that the first derivative was a constant. And if I know that the first derivative of a particular function was a constant, then it means that the original was a line. Okay. And that's how I end up getting this. Now, when we use reduction of order, we're not going to use this whole entire function here, meaning we're not going to use the root function with these constants. Okay. It is not important for us to actually include the constants. All we want is the root function, and for cx plus d, the root function is just x. Okay. So we're going to allow u to equal x here. Now, if you're not convinced, that's okay at this point. I'll show you once we're actually done with this problem what it would have looked like if we would have kept u like this, and you would have seen we still would have got virtually the same thing. Okay. All right. So now that we know that we're going to let u, which is u of x, just equal x in this case, because this is a root function for this outcome here, we now know that our y sub 2 function, meaning our other function that should be a solution to the ordinary differential equation, is just going to be x times e raised to the 2x. Okay. And of course, if I was to take x e raised to the 2x, and here I divided it by e raised to the 2x, what I end up getting is x. And of course, x is not a constant multiple. Okay. In other words, it's not a constant number. So the x e raised to the 2x and e raised to the 2x aren't constant multiples of each other. Okay. All right. So in general, our solution to this, our general solution to this second order linear ODE is just going to be y is equal to the linear combination of e raised to the 2x and x e raised to the 2x. And of course, what this means here is that depending upon what I want C1 or C2 to be, that would give me another solution to this ordinary differential equation. Okay. And these C1s and C2s would actually come from knowing the initial conditions that we would need to know to be able to find them. Okay. All right. So let's go back to what I was saying earlier here about u equals cx plus d. While we don't use all of this and we just use that u is equal to x, I'm going to show that down here. So had we actually done what you may have been thinking, which is let's just use all of this, then here you would see that this is our y1. All of this ends up being our y2. And of course, if I go ahead and work it out, do you see how I eventually get to a point here to where I have this constant times e raised to the 2x plus this constant times x times e raised to the 2x. And of course, C1 plus C2 times d, all that's a constant. So it really doesn't matter what I call it. It's just going to be a constant. And same deal here. C2 times big C is just another constant. So I'm just calling that K2 here. And so because of that, I still have a situation where I have a linear combination of e raised to the 2x and x times e raised to the 2x. So that's why it's really kind of redundant to go ahead and actually use this whole entire function here versus just using the root function. So that's why we just kind of clip it off and say, all right, well, whatever the root function is for you, we just use that and forget about the constants. All right, let's move to another example. Okay, so for our next example here, we want to kind of go through this whole process again. So we first want to verify that y sub 1 is actually a solution to this ODE. And then afterwards, we're going to actually find out what our other function that will complete our basis of solutions for this particular ordinary differential equation will end up being. Okay. All right. So first, let's verify y1 is a solution. Okay. So to do that, we know that we're going to need the second derivative here. So we know that the derivative of cosine hyperbolic, or cosh x, is going to be sinh x, or sine hyperbolic. And then from that, we know that the second derivative here, sinh, the derivative of that is going to be cosh, or sine hyperbolic. The derivative of that is cosine hyperbolic. So, of course, it's pretty easy at this point that I know that the second derivative is the same as what the original function is. So if I have this subtracted from itself, of course, that's going to be equal to 0. And of course, it's verified. Now, one thing I do want to go ahead and point out here before we move on, because it may kind of get lost in the sauce here, is that notice that if I was to let y equal 0 here, that y equals 0 would also satisfy this particular equation. Okay. And so one of the things I want to mention is that one of the things that is well known about nth order linear ODEs, especially the ones that are homogeneous, y equals 0 will always satisfy a nth order linear homogeneous equation. And so a lot of times we leave it off just because, hey, it's a trivial thing. We always know that works, so we leave it alone. However, please be mindful that you always have that solution, okay? And so let's say if you're taking a course of mine, one of the things I will do is have these equations be in here, but also throw in, hey, do you remember that this has this constant solution as well, okay? So I would say good practice is to go ahead and state that y equals 0 will always be a solution to equations like these. Even if you really don't need it, just to cover all bases there. Okay. All right. So now let's get into actually finding out what y2 is going to be. Okay. So we're going to say find what y2 is. Okay. So here we're going to let y sub 2 equal u times y sub 1, and remember here that u is going to be a function of x. Okay, so I'm just going to put that there to remind us of that. So because of that, I know that I need to find the second derivative here, but to do that, I got to go through the first. So y sub 2 prime is just going to be the derivative of the product of these two functions, which is going to be u prime y1 plus u y prime 1. And u prime, don't know what it is, so I just leave it there. My y1 is going to be cosh x, and then plus, don't know what u is, but I do know that derivative of y sub 1 is going to be sinh x. So now I need to find the second derivative. which is essentially just going to be the derivative of both of these two terms here. So for the first term, I'm going to take, and I'll write it out so that way you don't get lost here. So we're going to take the derivative of the first term plus derivative of the second term. Okay. And I'll drop down one more here. So for the first term, this is going to be derivative of first times the second. So the derivative of the derivative, the second derivative, times the second, plus first times derivative of the second. And of course, the derivative of cosh is going to be sinh. And then we repeat the process here at the second term. And so derivative of first times second plus first times derivative of second. Okay. So now at this point, we have the second derivative that we need. And of course, we know our original function. So therefore, we say that y sub 2 double prime minus y sub 2 is going to equal 0. And then I just substitute in all this for y sub 2 double prime. And then, of course, I'm going to substitute in this u times y1. And, of course, that'll just be u times, what's it, cosh x. Okay. So here, let me go ahead and rewrite all of this. Got that. And then, of course, minus what y2 is, which is just u times y1, which is cosh x. And, of course, all that equals 0. Okay. Now, at this point, as expected, all terms that have just u in it are going to cancel out with other terms so that we have no terms of u in our equation at this point. And so you can easily see that right here. So these two terms cancel out. Okay. Now, another thing that you see here is that we only have terms now in terms of u double prime and u prime. Okay. And of course, this means here that we have u double prime, and I'll just do cos x like this. And we got two terms that look the same. So this would be 2 u prime. And actually, I'm going to move that 2 on the inside there. Yeah, so let me do that right quick. All right, so we'll say this is 2 sinh x. And that's going to equal 0. All right, so at this point, notice that this is going to be an equation that can be separable here, but we're going to have to do a substitution to make it look like that. So we're going to say let v equal u prime, and that means that here v prime is going to be u double prime. Okay, and that in turn means that we have v prime times cosh x plus v 2 sinh x equals 0. And of course, from there, I could rearrange this equation here to have all terms with v on one side, all terms with x on the other. Okay. And so please note here that this v prime that you see here, even though we see this, what this really is dv dx. And it's going to be important for us to write it that way in doing the algebraic manipulation to make it easy for us to deal with it. Okay. So here what that means is I'll have this term and I could subtract this term from both sides. So I have dv over dx times cos x is going to equal to minus 2 sinh x times v. And then if I do some algebraic rearranging here, you'll see that I'll just have dv over v, and that's going to equal to minus 2 sinh x over cos x dx. Okay. And this is just minus 2 tangent hyperbolic of x dx. All right, so now at this point, we know that dv over v is just going to equal to minus 2 times tangent hyperbolic of x dx. And we know that we can integrate both sides here, okay? Now, of course, the left side is relatively easy to do. The right-hand side is relatively easy to do too, if you remember your derivatives and antiderivatives for your hyperbolic functions. So here we know that the left side is just going to be natural log the absolute value of v. The right-hand side will ignore the minus 2. And we know here that the antiderivative of tangent hyperbolic here is going to be natural log of absolute value of cosine hyperbolic. And that's very similar to saying that the antiderivative of tangent of x is going to be negative natural log of absolute value of cosine, okay? But notice that we don't have the negative there. Now, if you don't remember that, you can always deal with it in this form here of sine hyperbolic over cosine hyperbolic and use the substitution rule. And I'll go ahead and demonstrate that just so that for those of you that need to see it, you'll have it. All right, so let's say we're doing the antiderivative of sine hyperbolic over cosine hyperbolic here. And I'm just going to put the minus 2 on the outside like that. If we let w equal cos x, then this is going to imply here that dw is going to be sinh x dx. Okay? And of course, sinh x dx could just be replaced with dw, and cos x could just be w. So here, if we were to figure this out, then of course we would have minus 2 natural log of absolute value of w. And of course, this has some integration constant. And here we know that w was cos x. Okay. And so that's how we would end up getting the same thing there. All right, so at this point, we just need to solve for v. So what I'm going to do is we are going to take this minus 2 here and move it inside of the logarithm. So this will end up being natural log of absolute value of 1 over cos squared hyperbolic, or cos hyperbolic squared, which essentially is going to be secant hyperbolic squared. Okay. So here this would be natural log absolute value v, and this would essentially be this. Make life easy. And then what I'll do is subtract this natural log of secant hyperbolic squared on both sides. And this just equals to a constant. And then from there, this just means that we have natural log absolute value of v divided by secant hyperbolic squared all here, and then that's just equal to c. All right, and I'm kind of taking a different approach. I really didn't have to do this, but I'm doing it. So from this approach here, if I go ahead and make this an exponential equation, then I just have v divided by, absolute value of v divided by secant hyperbolic squared of x. All that's equal to e raised to the c, which means that all this without the absolute value signs is just going to be plus or minus e raised to the c, which means that v is just going to be a times secant hyperbolic squared of x, where a is just this constant here, plus or minus e raised to the c. So we're here, and we now know what v is, okay? But if you remember, v was the same as u prime. So therefore, v was the same as u prime, which we know is going to be du over dx, because remember, u is a function of x. And that's just going to equal what we have here, okay? And so essentially, all we need to do is to take the antiderivative of secant hyperbolic squared, okay? And fortunate for us, the antiderivative of secant hyperbolic squared mimics the antiderivative of secant squared, which is just tangent. So because the antiderivative of secant squared is tangent, the antiderivative of secant hyperbolic squared is going to be tangent hyperbolic, okay? So we recognize that this is a directly integrable type of equation here. And I guess to be technically sound notation wise, I'll go ahead and do this. And then of course, integrate both sides here. And the result, our u ends up just being a times tangent hyperbolic of x plus some constant, okay? And I think I've already used c, so I'll use c1 here, okay? And so that is essentially what u is, but we're going to say for simplicity, let u equal tangent hyperbolic of x. And so this is going to imply here that our y sub 2 is just going to be tangent hyperbolic of x, which I'm going to write as sine hyperbolic of x over cosine hyperbolic of x times y1. Because remember here, let's see, yeah, so let that be that. We come back up here. Remember that our y sub 2 is going to be u, which we just found, times y1. And remember our y1 here was sinh x. Sorry, not sinh x, cosh x here. So I'll come all the way down here, multiply it times cosh x. Of course, we see those things reduced to 1. And we see that our result here just ends up being that y sub 2, or our second solution, is just sinh x. All right, so now that we know that, our basis of solutions here, we're going to have y1, y2 for the basis of solutions is just going to be cosh x and sinh x. And the general solution for this ordinary differential equation here is just going to be y is equal to c1 plus cosh x plus c2 times sinh x. Okay. And of course, like I mentioned before, all of these types of differential equations, meaning the second order linear homogeneous, always has a solution of y equals 0. And of course, if you let C1 and C2 both be 0, then you'll essentially get that. And so that's part of the reason why they really don't explicitly state it. Because if I have an initial condition here such that it'll make C1 and C2 both 0, then you'll end up getting that horizontal line. Okay, but just wanted to make sure that you knew it was there. All right, so I have 3 more examples that I want to do for you. The first one I'm going to talk about here towards the end of this video, since this has already been worked out. The other 2 examples are going to be rather long, so I'm going to make separate videos for those 2 examples. And the reason why I'm doing these longer examples here is so that you can see all the things that you would possibly have to deal with at this stage of learning about differential equations in doing problems like this. So one of the things I like to do is to try to expose you to as many different things as possible, but also to see how those things that you may have learned in Cal A and Cal B and pre-Cal kind of all gel together to help you to be able to solve these types of equations. So that's why some of the examples I'm going to do in the next video sets are going to be a little long. But again, it is good for you to be able to watch this, to be exposed to that sort of thing. All right, so for this last example here, we want to do the same thing. We want to just pretty much figure out what our other solution is going to be able to create a basis for it. Okay. In this set of instructions, we're assuming that y sub 1, whatever they give to us, is a known solution. So we're not going to go through the whole process of verifying it now. We're just going to use what's given to us and do the problems. And so if you're wondering, all right, well, if I'm taking an exam or something like that, and they ask me to do reduction of order, what do I actually have to do? This problem is a good example of that. Okay. Now, again, you want to always read your instructions, because your instructor or professor or whatnot may actually ask for you to verify that that particular function that's given is a solution. But if you know that and they're like, hey, just do reduction of order to find the other one, this example here would be one where you would actually just do that at the beginning. All right, so we assume here that this is a solution. And so we're going to assume that our second solution here to this differential equation is going to be just basically u times whatever they gave us. Okay. Now, notice here that the type of equation that you're dealing with is going to be a second order linear homogeneous equation. It is second order because the highest derivative is a 2. It is linear because you have second derivative, first derivative, no derivative, and then that's it on the left-hand side. And then, of course, we see here that all the coefficients are either constants or functions of x. And, of course, the right-hand side here is either a constant or a function of x as well. Okay. And in this case, since it's 0, this is what makes it homogeneous. All right, so now that we have that, we need to take the first derivative and the second derivative of what this is going to be. Okay, so of course, in both of these instances, we use the product rule, and this is a result of taking the first derivative of y sub 2. This is the result down here of taking the second derivative. And again, for the second derivative of y sub 2, we're just taking the derivative of the first term times the derivative of the second term, and we're applying the product rule to both terms. And so that's why it's a little long. We get this result. From there, we are taking our results for y sub 2 prime and y sub 2 double prime, and we're going to substitute it back into our equations here. Okay, so we have y double prime, y prime here, and y. We're going to substitute all of that into these equations here. Now, remember that y double prime is going to be y sub 2 double prime. y prime is just going to be y sub 2 prime, and y is now going to be y sub 2, which is just u times x raised to the 4. So when we do that, this is what it looks like. So all of this is what y sub 2 double prime is. All of this is what y sub 2 prime is. All of this is what y sub 2 is. Okay. And I didn't write it here, but we are essentially doing this. Okay. Where again, this is y sub 2 double prime, y sub 2 prime, and y sub 2. Okay. All that here. So now from there, remember that since we have a homogeneous equation here, we are expecting to have a first order separable equation be as a result. Okay. And of course, the first thing that we're going to see is all terms with u will cancel out with other terms. And so we see that happening right here. The next thing that we'll need to do here is to say, all right, to get this to looking like a first order separable equation like we're used to, I'm going to have to let u prime equal v, and by default, that means that u double prime is going to be v prime. Okay. Now, I just made this note here to say that to get this into a form that's going to be a little bit more malleable for us to deal with, we know that I can divide both sides here by x, or I should just say x raised to some number here, because I want to divide both sides by x to the 5th. So when I do that, what that essentially does is it turns it into this equation here, which is a lot easier on the eyes to look at, much easier to deal with. And if I let v be u prime and v prime be u double prime, then I have the situation here, which in the current form that is in, it is technically a first order linear ODE, but because I have a 0 here, I could rearrange this equation to get everything with v on one side, everything with x on the other, and that's why it ends up being separable. So if I go in here and rewrite v prime as dv over dx, then you see after some rearranging that it really is a separable equation, and you can really see it at this point. And then, of course, we just take the antiderivative, or integrate and take the antiderivative of both sides and figure out what our final answer is in terms of v. And so, well, we need to figure out what v is, and then try to find our final answer. So, of course, over here, we're going to take the antiderivative. It's going to be natural log absolute value both times. I add this term to both sides here so that I can use my logarithm properties and rewrite it like this. Change our logarithmic equation to an exponential one. And that will give us just absolute value of product of vx on the left-hand side. And then using the absolute value properties, we can drop the absolute value signs here as long as we do plus or minus here. And we just let plus or minus e raised to the c be some constant. Okay. And so that eventually turns out to be that v is just a divided by x. Okay. But remember, we said v was u prime. So since v is u prime, we know that u is just going to be the antiderivative of v. And so we just go and find that. So since v was a divided by x here, the antiderivative of that is a times the natural log of absolute value of x. And so for simplicity here, what we will do is strip off the constants and just say the root function is natural log of absolute value of x. So we let u be natural log of absolute value of x. So what that means here is that my y sub 2 is just going to be what y sub 1 was times what u was. So x to the 4th times natural log absolute value of x. And thus, the linear combination of these two functions here will end up being what my overall general solution to this particular differential equation would be. So hence, y of x is just c1 x raised to the fourth plus c2 x to the fourth times natural log of x. Okay? And that concludes this example and this video. We'll come back with part 2 to work on those other 2 examples that I told you, well, part 2 and part 3 to work on those other 2 examples that I told you that are relatively long.